and welcome to Lesson 8C on logarithmic functions as inverses. A logarithmic equation is the inverse of an exponential equation, and our definition of a logarithm says that if b and x are positive numbers and b does not equal 1, then b to the x equals a can actually be written as log base b of a equals x. Basically, what's happening here is a logarithm finds an exponent. So let's take a look at this. We know that 9 to the 1/2 equals 3. Well, let's rewrite that in logarithmic form. That's log base 9 of 3 equals 1/2. And what that's asking is 9 to the what gets me 3, 9 to the 1/2 gets me 3. Here we've got log base 5 of 1/5 equals -1. 5 to the what gets me 1/5? 5 to the -1 gets me 1/5. We can also do this in reverse. Log base 2 of 8 equals x. I can rewrite that in exponential form as 2 to the x equals 8. And log base 3 of x equals -4 is 3 to the -4 equals x. So what I want you to look at when you've got log base b, please write base b of a equals x versus b to the x equals a, I want you to pay attention to where everything is. The base is always the base, right? The b always stays in the same place. And your x switches from the exponent in the exponential case to the answer, or the argument, in the logarithmic case. And your a switches from the thing that's on inside the logarithm to being on the other side of the equation in your exponential case. So that's how they always line up. So let's do some examples where logarithms can actually help us solve things. Log base 2 of 32, what I always want you to do first is I want you to set these equal to x. And then I want you to rewrite them in exponential form. So this becomes 2 to the x equals 32. Now, we learned last lesson that we always want to rewrite everything in exponential form in the same base. Well, 32 is 2 to the 5th, and we've got 2 to the x over here. So now I just drop my bases because they're the same, and I get that x must be 5. So log base 2 of 32 is 5. Here we do these same things, set it equal to x. I get 3 to the x equals 81. Rewrite the 81 as 3 to the 4th equals 3 to the x, therefore x must equal 4. Log base 4 of 4, set it equal to x. I get 4 to the x equals 4. Well, there's always a hidden 1 whenever we write a number, so we end up with just x equals 1. Here, log base 5 of 1, set it equal to x. You do 5 to the x equals 1. Well, 5 to the what is going to get you 1. Only 5 to the 0 is going to get you 1. So your x must be 0. Here, set this equal to x again. I get 6 to the x equals 1/6 when I write it in exponential form. Rewrite the 1/6 as 6 to the -1 equals 6 to the x. Therefore, x must be -1. Here, set that equal to x. We get 2 to the x equals 1/16. Rewrite 1/16. Well, 2 to the 4th is 1/16, or is 16, and then the negative would make it 1/16 to get the fraction. So we've got 2 to the x here, therefore x must be -4. Coming right on along, I'm going to set that equal to x. That becomes 9 to the x equals 3. Rewrite them both in base of 3. That's 3 to the 2x equals 3 to the 1. Therefore, 2x equals 1. Therefore, x must be 1/2. Here, set this equal to x. I get 6 to the x equals the square root of 36. Rewrite everything in the power of 6. So 36 is 6 squared. Well, you know what? Square root of 36 is just 6, right, guys? We don't actually need to do anything there. And then we get 6 to the x, so x must be 1. Here, set this equal to x. I get 5 to the x equals the 4th root of 5. Rewrite these in exponential form. I get 5 to the x equals 5 to the 1/4. Therefore, x must be 1/4. Moving right along, set that equal to x. I get 1/3 to the x equals 27. Write these in the same base. I like 3 for this one. So this is 3 to the -1, and then the x is still there, equals 3 to the 3rd. So -1x equals 3, so x must be -3. Here, set those equal to x. I get 1/2 to the x equals 16. Write them in the same base. That's 2 to the -1 times x equals 2 to the 4th. -1x must equal 4. Therefore, x must equal -4. Here, set that equal to x again. We get 1/5. Ooh, not 1/2, 1/5. Try again. We get 1/5 to the x equals 5. Rewrite them in the same base of 5. 1/5 is 5 to the -1. The x is still hanging out. Equals 5 to the 1st. -1x equals 1. Therefore, x must be -1. So, 2 more. Set it equal to x. I get 9 to the x equals the square root of 3. Rewrite in the same base. That's 3 squared. The x is still there, though. Equals 3 to the 1/2. So I have 2x equals 1/2. When I divide by 2, I get that x is, in fact, 1/4. Set it equal to x. I get 5 to the x equals 5 root 5. Couple ways to approach this. I can recognize that this is 5 to the 1 times 5 to the 1/2, which really is 5 to the 3/2. So we still have 5 to the x going on here. So my x must equal 3/2. All right, so to solve equations with logarithms, it's often useful to rewrite them in exponential form. So here I've got log base x of 25 equals 2. Rewrite that as x squared equals 25. I take the square root of both sides. I get that x equals just 5. Now, if you recall, we actually had to define at the very beginning that our b value could never be negative with logarithms. So that is why it's just 5 and not plus or minus 5. So do the exact same thing here. This becomes x to the 2/3 equals 4. In order to get rid of that 2/3, I raise everything to the 3/2 times 3/2. So I get x equals 4 to the 3/2. Well, square root of 4 is 2. Cubed gets me 8. So we do the same thing again here. I want this to be 1/4 cubed equals x, rewriting it exponentially. Cube all of that, and I get 1/64 must be my x value. Here, rewrite this as an exponential equation. I get 4 to the -2 equals x. Well, that would be 1/16 must be x. All right, we're doing a great job so far. A common logarithm, the common logarithm, has a base of 10. So if we don't specify a base, it is understood to be 10. So log of 1,000 is really log base 10 of 1,000. So when I solve that, I would set it equal to x. It would be 10 to the x equals 1,000. Well, 10 to the what gets me 1,000? 10 to the 3rd power would get me 1,000. Again, set it equal to x. There's a missing 10 right there that I don't have to write, but it is there. So that's 10 to the what gets me 1/10. Well, 10 to the -1 gets me 1/10. All right. So here I want you to find each specified value without using a calculator. Again, set it equal to x. So we flip it around. I get 2 to the x equals 16. Well, 2 to the what gets me 16? X must be 4, which means the value of this thing here is 4. Now, if you notice in the next problem, this dude shows back up, right? He's there. I already know that log base 2 of 16 is 4. So 2 to the 4th is, in fact, 16. Now notice, there's the 16, there's the 2, and there's the 2 again. There's a pattern going on here that I want us to spot here in a second. So we're going to set that guy equal to x. I get 3 to the x equals 1/9. Well, 3 to the what gets me 1/9? 3 to the -2 gets me 1/9, because 3 squared is 9, so 3 to the -2 would be 1/9. Now again, that thing we just solved for, it's shown back up. So I can actually plug that in as 3 to the negative 2, which gets me 1/9. And once again, boom, there's the 1/9. There's my 3 in 2 places again. So there's actually a pattern here. If I have b to the log base b of x, that is always going to be equal to x. It's a pattern. Similarly, if I have log base b of x, it's always going to be equal to x. Those are 2 shortcuts that you can memorize to make your life just a little bit easier, so you won't have to work it out every single time. So 4 to the log base 4 of 5 is just going to be 5. And 6 to the log base 6 of 2 is just going to be 2. Log base 3 of 7 is just going to be 7. Log base 5 of negative 3 is just going to be negative 3. That's that lovely shortcut we found. Log base 9 of 3, well, is going to, we actually could solve this one by setting it equal to x. So I would get 9 to the x equals 3. Well, that's 3 to the 2x equals 3 to the 1. So I get x ends up being 1/2. Okay. Log base 8 of 2, set it equal to x. I get 8 to the x equals 2, or 2 to the 3x equals 2 to the 1. So x must be 1/3 here. Log base 32 of 2, set it equal to x. I get 32 to the x equals 2, or 2 to the 5x equals 2 to the 1. So we get 5x equals 1, so x must be 1/5. And here, set it equal to x, I get 16 to the x equals 64. I'm going to set them both in terms of 4 because they are powers of 4. 4 to the 2x equals 4 cubed, which means x must be 3/2. All right, let's talk about graphing. Graphing logs is different than graphing anything else you've ever done, because you guys are going to think exponentially as opposed to logarithmically. That's just the way your brain has been taught. It's the way your brain is wired. So when you're thinking about your exponential or your logarithmic graphing, I actually want you to always rewrite this exponentially. So this becomes 2 to the y equals x. And then I want you to make your table with your x and your y. But unlike what we usually do, I actually want you to plug into your y side first because it's going to be a lot easier for you. We're going to plug in -3, -2, -1, 0, 1, 2, 3. Okay, so if I do 2 to the -3, I get 1/8. 2 to the -2 gets me 1/4. 2 to the -1 gets me 1/2. 2 to the 0 gets me 1. 2 to the 1 gets me 2. 2 to the 2 gets me 4. And 2 cubed gets me 8. Now graphing these, you have to be really careful because you're still reading x then y, even though we plugged in our y values first to figure out our chart here. So I'm going to go to 1/8 and then -3. 1, 2, 3 right here. Boom. And then 1/4, -2. Boom. 1/2, -1. 1, 0. 2, 1. 4, 1, 2, 3, 4, 2. And then 8, 3 is off. So when I then put those together, what I get is this curve here. My domain is my x values are always going to be greater than, but never actually equal to 0. And my range is all real numbers. And there is, in fact, an asymptote on the y-axis. There's an asymptote here at x equals 0. That's my asymptote. So let's look at another one of these. Let's do one that's got a fraction base. So again, what I want to do in order to be able to start this is I want to flip this into exponential form. This becomes 1/4 to the y is equal to x. And we're again going to plug in similar numbers to what we did before. We've got x and y, and we're going to plug into the y value this time. And I'm just going to do -2, -1, 0, 1, 2, because -3 is not going to fit. So 1/4 to the -2 is going to get you 16. And then 1/4 to the -1 gets you 4. 1/4 to the 0 is 1. 1/4 to the 1 is 1/4. 1/4 squared is 1/16. So again, being really careful graphing this. You've got to point at 16, -2. That's way off the graph. It'd be 16's way over here, -2's down here, not going to fit. 4, -1 on the other hand does fit. Then you've got 1, 0, 1/4, 1, and then 1/16, 2. And if we kept going, it'd be getting closer and closer. So your graph looks like this. I'm trying really careful here. Boom, that's your graph. So your domain is, again, your x values are always greater than 0 but not equal to 0. And your range this time is all real numbers, and your asymptote is still at x equals 0 along the y-axis. So let's generalize this a little bit. The function form of y equals log base b of x always contains 3 nice pretty points. The one that you're always going to remember, it's always going to contain 1, 0. Because b to the 0 is always 1, so 1, 0. You're also always going to contain b, 1, because 2 to the 1 would get me 2, right? 1/4 to the 1 gets me 1. So we had that 1/4 1 is right here, right? And then you're also going to contain 1 over b, -1. Those are your 3 pretty points. The domain is always going to be x is greater than 0 as long as we don't shift it, and your range is always all real numbers. And your y-axis is always an asymptote of the graph. Okay, it gets close to the y-axis without ever actually crossing it. So guys, I believe, yep, that is the end of this lesson. So go ahead and take a look at the homework. Thank you guys so much.